Welcome to the Topic 5 quiz. Question number 1 was pretty straightforward. It was Hess's law with just two equations. So when you look at it, you should notice that equation 1 has carbon on the correct side, CO2 on the correct side. Equation 2, though, you need to flip the MnO2 and Mn around, so that means you need to flip the sign here. And then adding these up as you add the equations up gives you the 130. Question number 2 was a little bit challenging for some groups. You've got the following data, and what you have to figure out is that you're being asked for the CF bond enthalpy. So that means you have to have each element in its gaseous state. So that means what we're really trying to add these up to accomplish is we want C as a gas plus fluorine to get CF4, and both of these as a gas also. So I need a 4 here to balance it. So as I look at this, CF4 is on the correct side. The 2F is on the wrong side, and it needs to be doubled. And then the C solid and C gas is on the wrong side. So what I really need to do here is I want C solid plus 2F2. That equation is fine, and on the other side I'm going to have CF4. And then for the second equation, I want to flip that over so that I have 4F and 2F2. And so I had negative 680 from the first equation. The second equation, I'm going to have 2, and I'm going to flip that sign to negative 158. And then the third equation I also need to flip, but I don't need to increase it. So it's going to be C gas plus C solid. And so I'm also going to flip that sign to negative 715. So when I add this up, I end up with C solid plus 2F2 plus 4F plus C as a gas, CF4, 2F2, and C solid. So my C solid crosses off each side, the 2F2, and I'm left with the equation I'm actually interested in. And then my value here is a negative something. Let me turn my page. Negative 1711. And that's for the CF4. So now to get just the CF bond, I take that 1711, divide by 4, and I find out it's negative 428 kilojoules per bond. Number 3, most of you got this right. They're just asking, does it make any difference if heat capacity is in joules per gram per Kelvin degree and your temperature is measured in Celsius degrees? So what they're really asking is, what's the relationship between Kelvin and Celsius? And the relationship is that 1 Kelvin is the same amount of energy as 1 degree Celsius. That 0 degrees is freezing on the Celsius scale, 100 is boiling, and on the Kelvin scale, 273 is freezing and 373 is boiling. And actually you don't use degree signs with Kelvin because you just had to be different. So it's a 1-to-1 conversion, so it's not going to affect it, and A would be the correct answer. Number 4, you're being asked which process has an enthalpy change closest to this value. So really what they're asking is, which of these equations shows just one CH bond being broken, or at least that's the net change for the equation. And A and C you can eliminate because you have carbon as a solid, so you have carbon in its gaseous form as part of CH4, so that would bring in some changes there as well. Since we're talking about enthalpy, I can just eliminate A and C right off the bat. So then B and D, when I look at it, CH4 becoming C plus 2H2, I have 4 CH bonds on the left, and on the right I do still have 2 H bonds, 2 single bonds. And so this is not a net change of a CH bond, but D is, because I would go from 4 CH bonds, and CH3 would have 3 CH bonds, and then the hydrogen as a gas would have no bond. So the net difference between your reactants and products is just that 1 CH bond, which you were asked to find. Question number 5 then says, the following equations show the oxidation of carbon and carbon monoxide to form carbon dioxide. What's the enthalpy change? And when they use X and Y, don't let it mess you up. You're just going to look at it and see which equations do you have to flip, if any. So CO2, I don't need, but C as a solid I do need. O2 as a gas I do need. So it would appear I can keep this the way it's written, so negative X. The second equation, the CO, I need on the opposite side, so I'm going to have to flip this. So I'm keeping the negative X, but this is going to become positive Y. If you do a quick check, you'll see you don't have to change the amount. So I'm really left with the negative X plus Y, which is the same thing as Y minus X, or letter C. Number 6 was pretty easy. The following equation shows the formation of magnesium oxide, and you'll notice this is negative 1204 kilojoules, so that's kilojoules per 2 moles of magnesium, 1 mole of oxygen, or 2 moles of magnesium oxide. So 1204 is released for every 2 moles of magnesium. 602 kilojoules of energy are absorbed. The negative lets you know that absorbed is not going to be in the running, so B is out of it. C, 602 kilojoules of energy are released for every mole of oxygen gas reacted. That's not true. It's negative 1204 kilojoules per 1 mole. So D is our only correct one, 1204 kilojoules for every 2 moles of magnesium oxide formed. Number 7, a simple calorimeter, which best explains this. They're just getting to the fact that IB always wants you to realize that heat loss to the surroundings is your number 1 source of air with any calorimeter. So if in doubt on a calorimeter, heat loss to the surroundings is your ticket. Number 8 says define the term average bond enthalpy. So for 3 marks, you have to mention that it's a mole of bond breaking. You have to mention everything is in a gaseous state. And then for the average part, you have to mention it's being compared to bonds in similar compounds. And then why isn't Br2 an example? Because there's only one Br bond there, so there's nothing to average it with. You'd have to have it compared to some other things to come up with an average. Number 3, using the values, I've written out what the bonds are here. I've got 4 CH bonds and 1 Br single bond, and then I'm ending up with 3 CH bonds, 1 CBr bond, and 1 HBr bond. So I really could look at the net here is the 3CH is really just a net 1CH over on the other side. So then when I plug in, I'm going to take my reactants minus my products, so I can plug in 4 times the 413 for the CH plus the 193 for the BR, and I'm going to subtract then 290 for the CBr, and then the 366 for the HBr, and when I do that, I got negative 50 kilojoules. As far as an enthalpy diagram, make sure you put potential energy or some label on this side, and if you draw it like IB does, make sure you label which line is reactants, which is product. The other way to do this would be to show it over time, and then the products would be lower than the reactants. And again, you need to label them, even though it seems to make sense, reactants would be first. And then number 4, without carrying out a calculation, suggest a reason how the enthalpy change for this reaction would compare. So again, I've got it written out, and if you take a look at it, again, my CH is going to reduce to just a net 1 CH bond on this side. And even though I have 2 CBr, I missed a CBr on this side, I've got 2 on this side and 1 on this side, so this reduces down to just 1. And I actually have the same net reaction, so my delta H is also going to be the same. Then scrolling down to number 9, butene, I'm going to stop and draw these, what these look like, so we can look at what the bond enthalpy value should be that we plug in. So taking a look at the drawing, the C4H8 only works if you have a double bond in there. And then O2 is also a double bond, CO2 is 2 double bonds, and H2O is the single bonds. So my net summary is 8CH, 2 single bonds between the carbons, 1 double bond, 6 double bonds in the oxygen. And then the carbon dioxide and OH bond each end up with a total of 8 because you've got 2 identical bonds and 4 molecules of each. So when I plug my numbers in, I have 8 times 412 plus 2 times 348 plus the 612 and then 6 times the 496. That's all my reactants, and I get to subtract my products, which is 8 times 743 plus the 8 times 463, and that gave me a net of 2068 kilojoules. And then part B of that, state and explain whether it's exothermic or endothermic. It's exo, and the reason why delta H is negative, the products were more stable, the products had less energy. You could have mentioned it's combustion reaction. Actually, I think I missed a question here. Let me go back. So now the process would be exothermic because delta H was negative, or the products are more stable, or because it's a combustion reaction. All those are good reasons for justifying it. And then number 10, I let you skip. So go on to the final page, 11 and 12, a couple of multiple choice. When 40 joules of heat are added and the temperature increases, this is as easy as it appears to be. I just need to plug into MCAT. I've got 40 joules. I'm trying to find mass. I've got 2 and 8. So this is going to end up being just 2.5 grams. And then the final question, which statements are correct for all exothermic? So these 3 statements are probably true for some exothermic, but the only statements that are true for all is that the enthalpy of the products is less than the reactants. The sign is always negative. It may or may not be rapid at room temperature. Rusting certainly occurs at room temperature and can be a very long process. So only 1 and 2 are always true.